This learning module provides an overview of Levee Engineering Analysis for FEMA's Levee Analysis and Mapping process. The topics to be covered in this presentation are Levee Definitions, the new Levee Analysis and Mapping process for non-accredited levees, and a summary of the technical procedures that may be used for a given levee system. Also, how the approach will continue to evolve. What is a levee? A levee is a man-made structure, usually an earthen embankment, designed and constructed in accordance with sound engineering practices to contain, control, or divert the flow of water so as to provide protection from temporary flooding. Earthen levees are made from earth or soil, which is compacted to make the levee as strong and stable as possible. To protect against erosion and scouring, levees may be covered with everything from grass and gravel to harder surfaces like stone, asphalt, or concrete. No levee is flood-proof. Levees may reduce the risk during certain flood events, but they do not provide complete protection from flooding. Levees can and do deteriorate over time and must be maintained to retain their effectiveness. There are three types of common failures: overtopping, breaching, and seepage. As you can see in these photos, levee systems look different because they're built and designed differently based on how they are being used, site constraints, material availability, and other factors. The new Levee Analysis and Mapping approach was not intended to be a holistic solution for addressing levees within the National Flood Insurance Program, as the LAMP work groups were not allowed to make overarching changes in the NFIP. LAMP was intended to review levees from a solely engineering perspective. Levee systems may be analyzed using one or more procedures to identify potential flood hazard risk on the landward side of the levee system. The alternative procedures have been created to comply with all current statutory and regulatory requirements governing the NFIP, be a cost-effective, repeatable, and flexible approach, leverage local input, knowledge, and data through proactive stakeholder engagement, align available resources for engineering analysis and mapping, and consider unique levee and flooding characteristics. Each levee system will be reviewed and local input weighed for FEMA to determine the approach which will be applied to determine the landward side flood risk. The resultant flood risk depicted on the flood insurance rate map panel will indicate the most conservative or each of the procedures used along a levee system. All available procedures will be reviewed for application to a levee system to best determine the flood risk in the vicinity of a levee system. There are four aspects to the new approach: interactive stakeholder engagement process, including a local levee partnership team, a more robust levee analysis and mapping procedure, recognition of the uncertainty associated with levee systems, and analysis of levee reaches. FEMA, through its mapping partners and contractors, may perform a limited data analysis of the levee system to develop baseline estimates and expected ranges of the special flood hazard area extent and depth. During this phase, FEMA will select depth profile locations to communicate the variability in expected depths resulting from the various procedures as shown below. This initial quick analysis will provide an early indication of what the results from various types of analyses might provide and some indication which procedures could most effectively depict the flood hazard. From the stakeholder process, analysis and mapping procedures can be selected that best reflect a community's unique circumstances and local flood hazards. The following suite of new procedures have undergone an extensive process of scientific review and public input: sound reach, freeboard deficient, overtopping, structural-based inundation, and natural valley. The sound reach procedure is used for a levee reach designed, constructed, and maintained to withstand and reduce the flood hazard posed by the base or 1% annual chance flood. No levee reach specific modeling is required for a sound reach. However, it's important to note that the special flood hazard areas from the system-wide interior drainage analysis and/or adjacent levee reaches may still be present landward of the sound reaches. This will depend on the presence of interior ponding areas and other terrain features on the landward side of the levee. The following slide explains what a system-wide interior drainage analysis is. The interior drainage of a levee refers to the outflow of streams or runoff that lie on the landward side of the levee. In some instances, this outflow of landward flooding sources may pond behind the levee. For non-accredited levee systems with a potential for measurable flooding on the landward side of the levee, the adequacy of interior drainage systems will be evaluated and a special flood hazard area will be mapped for the 1% annual chance flood in these locations. The level of effort required for the analysis will depend on the procedure chosen for the levee reaches within the system. Interior drainage systems associated with levee systems usually include storage areas, gravity outlets, pumping stations, and contributing watercourses. Analysis using the sound reach procedure must also examine the potential for flood waters resulting from upstream levee systems and reaches that do not meet all the requirements of 44 CFR 6510 and are therefore not considered sound. It must also include an interior drainage analysis for backwater areas resulting from larger streams downstream and areas drained by pumping systems. This graphic is an example of the mapped flood risk areas typical of a levee system for which the sound reach procedure has been used. Note the sound reaches as marked by a dashed green line and the deficient reach shown by the dotted red line. Given the potentially catastrophic consequences of a levee system overtopping and failing, freeboard is an important design standard. Freeboard refers to the vertical distance between the top of the levee and the base flood elevation. Federal requirements generally call for at least 3 feet of levee freeboard, while allowing a minimum of 2 feet in some instances. A levee whose top is greater than the BFE but does not meet freeboard requirements may be considered freeboard deficient. Landward flood risk from the freeboard deficient reach is designated as Zone D and estimated using the natural valley procedure. Special flood hazard areas from the system-wide interior drainage analysis and/or adjacent levee reaches may still be delineated landward of freeboard deficient reaches. In addition to the freeboard deficient reach, the analysis must also examine the potential for flood waters resulting from upstream or downstream levee systems or reaches that do not meet all standards of 44 CFR 6510. Additionally, interior drainage must be assessed and mapped appropriately. This graphic depicts a combination of interior drainage and other flood risks areas that may be combined to map a levee system with a freeboard deficient reach. The overtopping procedure is appropriate for levee reaches that are known to overtop but not appreciably erode during the 1% annual chance flood as verified by a professional engineer. The BFE is calculated to exceed the height of the levee crest at a minimum of 1 location along the levee's reach length. For an overtopping reach, technical analyses will be performed to determine the volume of water that will overtop the levee during the 1% annual chance flood event. The volume of water will be used to establish the special flood hazard area. The overtopping procedure determines elevation and location where the levee is overtopped during the 1% annual chance flood event, length of time that overtopping occurs, and the average flow rate overtopping the levee. This graphic depicts an example of flood risk areas that may be mapped after using the overtopping procedure. The structural-based inundation procedure is appropriate for levee reaches with either known structural deficiencies or lack of data to support one of the other procedures. FEMA will rely on modeling of breaches along the levee reach. This method does not predict timing and location of a levee breach. This method does determine the likely volume of water and duration that would escape the river channel if the levee did breach. A breach analysis consists of different methods to identify possible locations of system breaches, modes of failure, geometry, failure triggers, and failure duration. In the structural-based inundation procedure, multiple breaches are modeled and mapped, resulting in a composite special flood hazard area. In the examples shown, there are 3 breach locations with resulting mapped special flood hazard areas. The term natural valley refers to the river channel and floodplain of a river system prior to the addition of flood control structures and construction of levees. For this procedure, discharge is allowed to flow on either side of the levee. The natural valley procedure will be used in 2 ways. First, landward of the entire levee system to determine the outer limits of any Zone D areas used, and second, as a potential procedure applied to individual levee reaches to determine the special flood hazard area on the landward side of the levee reach. In some cases, the natural valley procedure may only be used to understand the maximum extents of the Zone D areas. However, if the natural valley procedure is selected to actually map the special flood hazard areas, the flood elevation determined by the natural valley procedure will be mapped on the landward side of the levee system to describe the anticipated extent of flooding during the 1% annual chance flood event. When the natural valley procedure is selected, the flood hazard area will usually be designated as Zone A or AE. A levee reach is defined as any continuous length of a levee system to which a single technical procedure may be applied. In other words, a given levee system may be subdivided into several reaches, with each reach having a different technical procedure applied. The determination of the procedure to be applied will depend on factors such as available data, hydraulic conditions, community needs, and funding availability. The degree of information necessary to perform a given type of levee analysis will vary. The following table summarizes required and recommended information for each of the procedures discussed in this presentation. The FEMA levee analysis and mapping procedures will continue to evolve. The agency is aware that the LAMP approach requires more interaction between FEMA and local communities and is committed to understanding their knowledge and operation of a levee system and collaborating to determine the appropriate LAMP approaches. Key documents will provide the communities, levee owners, and local project sponsors with a clearer idea of how their participation will be accommodated in the new process. The agency will engage with pilot project communities to document their applications of LAMP, refine the standards and guidance for implementation, and prepare educational and training materials for future communities that will be engaged in LAMP. With the passage of the Biggert-Waters Flood Insurance Reform Act of 2012 and the long-term conclusions and recommendations from the National Academy of Science report, information and guidance will continue to emerge that can affect FEMA's approach to analyzing and mapping levee systems. FEMA plans to implement LAMP on a larger scale across the nation in future years, applying the lessons learned in the pilot projects. Visit the following webpage to access additional information regarding FEMA's revised levee analysis and mapping procedures. For more information, please contact the Risk Communication Specialist or consult the resources shown on the slide. This concludes our presentation on levee engineering.